Hey everyone, I recently gave a talk at a meetup in London on reasoning, and a lot of people came to me after the talk and said they liked the slides. Do you have any more information? So I decided just to re-record this talk just because it might be of wider interest. And yeah, might be able to go into more details as well than I did in the 20-minute version in real life. So here it is, the Hitchhiker's Guide to Reasoning. So name of the talk is obviously inspired by Hitchhiker's Guide to the Galaxy, and there's a famous, bit of that story where humans have this very difficult problem. They want the, answer to life, the universe, and everything. So they build a very big computer to try and solve that problem. They ask the question. The computer thinks for a long time, 7.5 million years, and then eventually comes back with the answer 42. Now, I like this example because I think it contains all the key elements that we care about in reasoning. On the one hand, we have a difficult question that we want a computer to solve. The question is so difficult that the computer needs to think about it for a long time, and which scales with the complexity of the problem. And finally, in this example, it gives an answer that we can't interpret, right? So, a big theme in reasoning in the future, as these machines become more powerful, is can we even interpret both their inner workings, but also the answers they give to us. But I thought I'd start maybe just by going over the definition, because people on X and other places, they really fight over reasoning. People care about it a lot, so I just want to really simplify it so we're on the same ground first before we continue. So undoubtedly there'll be other definitions of reasoning that I'm not capturing in this, but I just want to focus in so we can target one aspect of that. So I'm going to approach this by saying that reasoning is the process of drawing conclusions by generating inferences from observations. So the three key components we care about are conclusions, the things we want to get, observations, which is kind of the question and the kind of constraints we're given, and the inferences, which take us from the observations to the conclusions. So we take a really basic problem. Jane has 3 apples. She gives 2 to John. How many apples does she have after? In this case, that would be the question. The inference steps would be, after giving 2 apples to John, she has 3 minus 2, 1 apple. And then finally the conclusion is, so she has 1 apple left. So this, kind of tells you how a reasoning problem is structured, even in this very simple case. But even as you extend to a very complex problem, these 3 components still remain. Now, if you want to go, talk about this more formally, you can kind of interpret this as a generative model. So we have a model that wants to generate conclusions and inferences given some observations. And you can kind of break that down a bit. So, on the one hand, you want to generate inferences based on the observations. And then given those inferences and observations, you're going to draw a conclusion. So that just shows how you can break it down to something generative. But of course, we don't just care about any conclusions. We care about the right conclusions. So good reasonings when we generate inferences that lead us to the correct conclusions. So one way you can think about this is, if we start here on the left, we have a probability of a conclusion, and we want the conclusion to be the right conclusion, which I've denoted as Y star here, given the observations. And we can think about this as an expectation of our inference steps. So with an expectation, what we're going to do is going to have our integral integrating over lambda, which is our inference steps, and we're going to weight this guy here by the probability of an inference step given an observation. And this term here, the probability of generating the inference given the observation, that's really the key kind of term we're going to want to try and optimize with kind of reasoning models. But what this tells you here is that if you sample, let's say an LLM, multiple times, you'll get different inference steps, and the expected chance of getting a correct answer is represented by this term. So, and very crudely, you can kind of think of the problem as okay, you're trying to maximize the probability of being correct given the question, and you can think about the control variable you have as your inference steps, those things which take you from your observation to your conclusion. And really all reasoning research, no matter what method you look at, really boils down to how do you generate these inference steps lambda. So whether you're doing chain of thought, Monte Carlo tree search, any kind of method, it all boils down to this central question. So hopefully that simplifies things. So let's begin And this is an LLM focused talk, by the way, but let's begin with the simplest approach possible to doing reasoning, which I'm calling here direct inference. So in direct inference, we directly prompt for the answer without generating any inference tokens. So this is kind of how people first used to play with LLMs. There was no like chain of thought. People would usually just like put in a question and expect the model just to pump out an answer automatically. So here we have a physics question, and we don't need to go into the details of this particular question, but the key thing to notice here is like we've got a question, we've got some multiple choice answers, and essentially all I'm going to do is I'm going to prompt answer and colon, and then expect the LLM to generate the letter option, so A, B, C, or D. So just to stress, the model is not going to generate any working out chain of thought, anything like that. It's simply just going to like pump out A, B, C, D, or whatever the letter options are. So you can think about this as inference, and inference is a very loaded term here because I mean inference as in predicting, but also inference as in reasoning. But that's something worth thinking about. We can think about this as inference for a forward pass. So we have here tokenized our question where we've like appended at the end this answer colon. That's going to be, say, X tokens when we tend to tokenize it. We then put this through the layers of our transformer, and then the final layer is going to output a probability over different tokens. But given the training of the model, we're expecting it to output either, let's say, A, B, C, or D. Now, from a compute perspective here, you can think about it as roughly as follows. So using very rough transformer math, like a forward pass for a transformer is around 2n for like small input contexts. So n is the number of parameters in the model. So let's say you had like a 70 billion llama model, then the forward pass flops would be roughly 140 billion for a forward pass on a single token. But note in this case we have X number of tokens that come through this input. So roughly the flops here is going to be 2 and X. Now the reason I've just gone through that kind of like approximate transformer math is that the key problem with direct inference is this fixed compute bottleneck. So given like how many tokens you have in the question, you have fixed flops. So this works well with associative pattern matching. If you ask the question like, what is the capital of the UK, London, these like very like, you can always think of it a bit like a dictionary where you have some kind of like locality sensitivity. You don't really need any intermediate steps there. It's just like things which kind of like co-occur together are very easy to learn. But as soon as you move on to kind of questions where you need manipulation and maintenance of state, like intermediate steps, which tends to be like mathsy questions, this is where like the fixed compute really like hits you. And what you need instead, ideally, is to roll out more compute, ideally adaptively, given how much intermediates like you need, right? Because an alternative would be maybe just like train like a massive model with more layers, but then that would also be inefficient, right? Because then what if you have a simple question that doesn't require all that compute? So the ideal adaptive compute would be that you can just roll out compute as you need it at inference time. So that brings us nicely on to chained inference, which is where we generate inference tokens before we generate the answer. So this takes us more to what people are familiar with today. Now, these ideas became popular in 2021, 2022. Scratch pads was one approach. Chain of thought is probably the most dominant way we think about these things now, but also supervised approaches. So we tried this idea called work, which is like a supervised approach to reasoning, which I'll cover in a bit. So now taking that same physics example now, the key difference is that we're generating these inference tokens before we get to the answer. So, working out, to use like something more colloquial. Now, the key way to think about this now is that as well as like the tokenized input, which, this is kind of, ideally we'd have more left to right tokens here for the input just to be consistent. But now we're getting away from this 2nx constraint and having an additional amount of like thinking tokens through these inference tokens. So here, if we look back here, the first steps are, electricity is conservative. We got here the first token predicted electricity, then the next token is, and that's essentially allowing us to throw more compute at the problem through these inference steps. So before we get to this answer colon, we've actually used a lot more computes than we had before. So just side by side, before we had this fixed compute bottleneck, this 2 and x, but now by like doing this chain inference approach, we can like increase that to 2n times x plus t. So this is enabling adaptive compute. But this isn't the whole story, because even if a language model generated, let's say, 2,000 tokens before it got to an answer, that means bugger all if the actual tokens are garbage, right? So we need to discover good inference steps. So there's different approaches to doing this, and I would say this gets now to the core of what reasoning research is. So the first approach is prompting. So chain of thought originally was like a few shot approach. You'd put like examples of reasoning in a context window, but then it kind of turned to something more zero shot, where you could just say something as simple as let's think by step. And what this is doing is it's trying to like incentivize the model to break down things into step before answering. An alternative is supervised fine-tuning. So instead of like trying to learn in context and trying to retrieve procedural knowledge from pre-training, the fine-tuning approach is trying to impose it in post-training. So this is something we did with Galactica back in 2022, where we tried to do imitation learning of something that was more closer to internal reasoning, the kind of things you might do in your working memory on a scratch pad, those kind of approaches. And then reinforcement learning. So in these approaches, we're trying to change the objective function, using reward models, but also other kind of approaches, Quiet Start, O1, where you're really trying to learn, again, internal reasoning tokens, but instead of using fine-tuning, you're now like moving to a world where you're incorporating a reward signal. Now, it's worth talking briefly about what some of the main problems are with these kind of approaches. So one key problem is the missing intermediate problem. So the way to think about this is chain of thought, these kind of approaches, they're retrieving procedural knowledge or like templates that they've seen in the training set. And the majority of these are going to be like things that you might see maybe in like a textbook, right? So imagine like a high school physics, book where there's like an example, and here's a example, answer. That's the kind of knowledge it's retrieving. But the problem with these kind of answers is they typically skip steps for the sake of exposition. To give you an example, imagine that you have a physics question where you need to use a calculator. Or maybe if you had a laptop, you'd use Python. Now, would you see in a textbook answer all those explicit steps where someone's like opened up a Python terminal, a terminal, or they've used a Python interpreter or calculator? Like all these kind of steps are missing. Even steps that you perform in your working memory, supposedly trivial things, often they're not written down, because if they were written down, it would mean like an answer would be incredibly tedious, maybe like 5 to 6 pages, right? Which isn't great for teaching humans. So the examples of missing steps, they include steps performed in working memory, steps that maybe you perform on a notepad, or maybe like a Google Doc or something like that. Steps performed like using tools. All these kind of things are quote unquote missing in these kind of answers. That's not to say that examples of this procedural knowledge is there in the training set. It like almost certainly is, but it's not in this kind of nice like format that we want, that would be help us like use compute more effectively at inference time. So let me show you an example of like pathologies that arise from the missing intermediate problem. So in this case, we have the same question that we've been using, this physics question, and the language model has generated the following. The answer is A. This is because. So this is an example of conclusion-first reasoning. So you can see this might be problematic for an LLM because it's moving it back to a direct inference mode, not like a chained inference mode, because it's predicting the answer is, and then as soon as it gets to A, it's not generated any inference tokens. It's just predicting. And then typically what happens is that if the model guesses incorrectly, the inference steps after would then just be like kind of bullshit, like post-rationalization of why it said something. So we'd have often, in the old days, we'd have these amusing examples where I might say the wrong answer and then try and justify absurdities like 1 equals 2. This is what LLM research used to be like in 2021. Fortunately, it's a bit better now. But note that this isn't, in the real world, this is not like a bad thing, right? Like imagine a colleague says, can you work this out for me? And I go away, I solve the problem, I come back and I say, oh, well, actually what we should do is this, and this is because. That'd be a perfectly rational thing to say. But the key thing is I've already done the work before I've said the answer. Whereas an LLM hasn't done any working out here before it's done this. A second problem is kind of one-shotting like these complex calculations. So in this case, if you saw something like this in like a textbook, almost certainly the author has like used a calculator or Python script before they've done this. They haven't done it in their head unless they're super crazy or something. So this is another case of kind of clinging too close to the training corpus. Ideally, you want the model to break the problem down into smaller steps, or offload to tooling or something like that. So as it says on the slides here, this kind of behavior, trying to predict these kind of tokens which require a lot more compute, it just leads to more error-prone reasoning. So I just want to briefly cover something that we did back in 2021, 2022. So we were exploring these ideas, and something that was very apparent to us is like, can we actually try and like really write down everything that someone would do to solve a problem, right? So that means anything they do in their working memory, anything they'd write down on a scratch pad, even if they'd use like Python or something like that. So we created this high quality data set of reasoning traces where we broke down steps, always like avoided conclusion first reasoning, so always going the correct way, and then we fine tuned on this data set. So we originally did this in Galactica. We used it as like a special token, you'd prompt like work. But then we kind of scaled the same approach for Llama 3 SFT reasoning. So we'd have human annotators and we'd have like very explicit instructions like to them. So be super explicit, anything you use to get to the answer, write it down, never skip steps. And this led to kind of longer reasoning traces. But this was great for us because it's kind of using more computer inference time in an efficient way. But crucially, like never skipping any step. And what was really interesting is that even in 2022, we could see this trade-off between inference compute and training compute. So if you compared like a model at the time, Palm 540 billion chain of thought. So Palm 540 billion was trained with 33 times more compute than Galactica 30 billion. But what we saw is that if we use this kind of work approach for Galactica 30 billion, it would outperform this much larger problem on MLU reasoning like 36% to 19%. So that's quite a big difference. So I should caveat that this is very apple and oranges because these models use different pre-training corpuses, like the Galactic corpus maybe was better quality, but this is good evidence for explicit reasoning. So often, rather than just throwing more training compute at a problem, if you just get the model to be more explicit in the way it reasons, it can kind of use its knowledge more effectively. So this was back in 2022, even before these things became popular. But the problem with these approaches where we try and teach this behavior in a supervised way is that you need lots of human annotation to generalize well. So it's just a not very scalable approach, and it becomes even less scalable as the problems become more complicated. Because let's say you go to like PhD level problems, like increasingly the number of people that can actually annotate these kind of problems well like diminishes drastically, right? So the models, they're still imperfect at breaking down problems. And I just want to highlight something else as well. Even where you teach a model to like break down a problem into every steps you used, there's still a tendency for the model to reason inflexibly. So if you have no examples in your kind of like reasoning traces of evaluating, checking your work, backtracking, exploration, then ultimately the answers that an LLM spits out, they still resemble kind of textbook answers, not the real internal reasoning that we want to capture. So that's worth bearing in mind as we go into the later parts of this talk. Okay, so let's go on to reinforced inference. This brings us closer to the present day. So very close to chained inference, but now we're going to generate inference tokens and we're going to reward ones which lead to correct conclusions and punish the rest. So the key thing we're changing here now is we're really trying to optimize the right objective, because pre-training is kind of a maximum likelihood objective, even fine-tuning is, but in reinforcement learning we're trying to get a much sharper signal. So just to explain, you can think of this as kind of an objective mismatch, in the sense that the maximum likelihood objective, you're imitation learning on these kind of reasoning traces, so you're predicting the next inference step given the ones that came before. Whereas the real objective you want is you want to increase the probability that the model gets to a right answer given the inference steps. That's not to say these objectives aren't linked. In subtle ways they are, but the reinforcement learning objective just gives you a much cleaner outcome. In particular, one way to think about this objective mismatch is that your pre-training is kind of for recall and your post-training is for precision. So base models typically have very strong recall and reasoning problems. If you take a very old model like Galactica 2022, which is now like a Bronze Age model, if you sample that 100 times on GSM-8K, it will usually get the answer once in those 100 trials. So we tested this. I think the SFT version of Galactica got 99% oracle accuracy when you sample 100 times, right? So what that tells you is that the recall is very good. These models, even the old ones, they have knowledge of how to solve the problem. But then these models typically have very weak precision on reasoning problems at the frontier. So this older model on GSM-8K in 2022 was only getting 45% zero shot, right? So again, just to stress, if you sample 100 times, the model gets 99% if you have a perfect verifier. But if you have a zero shot on the same model, it's getting 45%. So weak precision. So really one way to think about post-training now is by optimizing the right objective function, we're going to improve the precision of the model so it gets to the answers more reliably. So one popular approach in the research literature is that we're going to model the objective with a reward model. This isn't necessary always because, if you have the ability to regex the answer from a ground truth, you can just use that feedback directly. But the idea about a reward model is that it's potentially more reliable, and also you can apply it to problems where you might not have a ground truth. So several papers on this. I've highlighted them here if you want to check them out. So I want to focus on one of these, which is outcome reward model. This is the simplest type of reasoning reward model, but it's also a workhorse and this takes you a long way. So the way this works is that you have an LLM and you also have a data set of questions and answers. Let's say high school physics questions. And then what you're going to do is you're going to use your LLM to generate some solutions for those questions, and you're going to mark with a ground truth. So in this example, I've generated 3 solutions. This one's correct, this one's incorrect, this one's correct. And then what you're going to do is you're going to train a reward model. So the reward model, the way it works is you take your LLM, you remove the head of the LLM and replace it with just a binary classifier which says correct or incorrect. So what you do actually is that, for this solution here where it's correct, what you're going to do is for every token in that solution, you're just going to give the final outcome. So if the whole answer was correct, then every token in that inference kind of trace gets a 1. If everything was incorrect, it gets a 0. So this is an example of sparse feedback in the sense that you're just punishing the whole thing if it's wrong. But note that's losing some information because typically there might be some right steps. But this is a very simple approach and it scales well. So I just want to show how this works in action. So just to go back here, we have the reward model that we've trained. And now we're going to see, can it correctly identify mistakes and also give us an indication of the probability of the model being correct. So here we have a GSM-8K problem. So Hunter counted 50 cars in the car park one morning. He counted 20 more cars. During lunch, half the cars had gone. How many cars were left? So, fairly simple. So 50 cars, counted 20 more cars. So that's 70. Half the cars had gone, 35. So, 35 cars were left. So here's an example answer from our old model. So the second morning, he counted 50 plus 20, 70 cars. So that's correct. 35 cars had gone, correct. The number of cars left is 35, correct. But then the model generates the following. When he got out of lunch break, he counted 35 plus 20, 55 cars, which is the final answer. So that's complete nonsense. So the way I like to think about this is there's a correct reasoning path. But the model, because in the pre-training phase, it's trying to stylistically learn what reasoning is. it sometimes gets into this like statistical pattern matching mode and just like veers completely off track. But the cool thing is, like in this example, the mistake is noticed by a reward model. So on this graph here, on the x-axis, I have the token step for the inference steps you just saw. And we also have the probability of correct answer on the y-axis. So this is the number outputted by the reward model. And you can see here, it's like kind of hovering up towards the end. So it's getting more and more likely, but then it goes off a cliff towards 0. And I've got the examples here of the individual tokens. So as soon as it kind of realizes it's doing this additional like nonsense step, the probability falls from like 68% down to like basically 0 fairly quickly. So that's great. That's the kind of behavior we want. Now, a bonus approach, I kind of highlighted this a few minutes ago, is that outcome reward models, they are a sparse type of feedback. So essentially the solution gets all zeros or all ones for every token. But as we mentioned, like what if like the first step was correct, but it was only the second step which was incorrect? So one way you can get this more granular kind of signal is an approach called Monte Carlo policy evaluation. So this was actually being tried out recently this year under various other names like Math Shepherd, all this kind of stuff. But this is actually just a very old RL approach where you're just interested in estimating a value function for a policy. So let's say your language model has a step. The second morning, he counted 50 plus 20 equals 70 cars. So in this case, we want to get the value of this step. So what you can do using Monte Carlo is you prompt the model with this step and you sample multiple solutions to the end. So in this case, the first thing we sampled is correct. The second one generates incorrect and the third correct. So 2 out of 3 are correct. So the expected value of the option here or step is 2 out of 3, 0.66. Now obviously you probably want to sample more if you wanted to get something more accurate, but that's going to give you the value of that step. So if you compare that to the outcome reward model where you're applying all zeros or all ones, using these Monte Carlo approaches, you could actually train the reward model with something more granular, where each maybe step would have something between 0 or 1 based on that policy. So these kind of approaches of reward models, they led to very good gains. So really for the Llama 3 work we did, like the bulk of the approach was via ORMs and these Monte Carlo approaches. So on math, that takes you from pre-training to post-training, gives you about a 20% boost. TSMAK, which to be honest now is pretty much solved by pre-training anyway, but even there you get a good boost too. So really the thing to stress, I think, is there's a lot of gains to be had by scaling these relatively simple approaches. So just to crystallize this whole thing, it's just by optimizing the right objective through RL, introducing this information about correctness, the outcome, just scaling that approach is a very successful approach. If you're trying to apply kind of reasoning approaches to your application, I would generally advise start with these kind of reward model approaches to begin with. Okay, but let's go further. So what kind of new ideas are there which take us beyond this kind of simple, PPO or whatever with these reward models? So here's a problem statement. Models fail as soon as they make mistakes. So this is what we talked about, where they resemble these textbook answers. And in a textbook answer, you never see the author saying, oh, actually, that's wrong, or actually, I'm going to try this. If you saw that in a textbook and someone's just literally putting their reasoning, you just think, I don't trust this person at all. They don't actually know the answer, right? So from the point of exposition, that would be bad to see. But from the point of internal reasoning, you don't just want things to fail when you make a mistake. You want them to try again until they get the right answer. So we want to incentivize models to explore other options and backtrack instead of just terminating. And the problem with termination is that if you think about it, it bottlenecks compute. If the model just terminates early, then we're not actually utilizing that extra compute to find another solution. So we want to, if you unhobble the model just to get rid of this kind of compute bottleneck and incentivize the model to continue even if an existing approach isn't working. So that brings us back to this graph, the reward model. So in this example, we saw that the model identified where the model made a mistake. So ideally, what we'd like to do is just to say, or actually, there should be a big stop sign with that approach, and then the LLM instead should then try and keep going along the road and try another approach. So the great thing about these kind of reward models or value networks is that they're going to give us an information basis to teach the model to branch and continue using compute to find another solution. But something we need to talk about is what's the action space we're kind of like planning over or generating over. So in LLM, the action space is tokens. But actually, when we think about ideas like branching, what we really want to branch over is something more abstract than tokens, which is like the notion of an individual inference step, right? So an example would be, if we saw the LLM generate, we use Newton's second law, then that might be like the kind of action space we want to try, right? Instead of the individual tokens like we or use. That's not to say you can't use token space to do these kind of things. It's just to say that maybe it's more efficient to think of these like higher level concepts that we want to plan over. So in the RL like kind of phraseology, an option would be like what a composition of tokens is. And in the context of LLMs, an option is going to be a collection of tokens. The simplest approach actually is just to say a new line is an option. You can fine tune the model to get to this kind of mode where each step would be like an individual sentence or an individual like new line. But that just gives us a simpler way to do these kind of things of branching and evaluation. So just keep that in mind as we do the next couple of slides. Now, types of options. So I want to posit that looking at this like higher level action space, these macro actions, there's different types of option. So one option is continuation. So that would be, you already have some steps and now you just want a new step for the same like direction that you're going in. So as an example, we can subtract 3 from 2 to get 1. I think that should be subtract 2 from 3 to get 1. So that would get a bad reward model score. Then termination would be where you generate conclusions. So the answer is 1 apple. So that's a type of step. And then evaluation would be where you generate tokens that kind of reflect on whether the current direction is working or not. So if you saw something like, that doesn't look right, then that would be an example of evaluating, checking your work. And then finally, exploration. So this would be that kind of branching behavior where we're saying, okay, alternatively, we can try this approach, or maybe we could try that approach. So just keep those options in mind. Now, let's think about this problem that we've been talking about throughout this whole talk, the missing intermediate problem. What kind of options are common in pre-training? So when we think about these 4 we've just gone through, because they're like kind of more textbooky answers in pre-training, we're going to see examples of continuation, right, the individual steps. And we're going to see examples of termination, like the conclusions. But as we mentioned before, we're not going to see examples of evaluation or exploration typically. So the model is going to be heavily biased towards this kind of procedural knowledge where it either continues or terminates. And that's problematic because, as we said before, this is going to lead to a suboptimal use of inference compute, right? We don't want it to terminate immediately after applying a single approach. We want to try another approach, right? And not only do we want to try another approach, we want to use the knowledge of what's worked and what hasn't to guide what to explore on the next go. So that's a really key point. But you might say, okay, why explore, right? So, if the model gets the first attempt wrong, maybe it's always going to be wrong. But I actually want to say something more provocative, which is that LLMs, they know everything if you sample long enough, right? So the clarifying statement there is like, if you have a good enough verifier, right, eventually you can pick out the gold. So one way we can test this kind of idea of the power of sampling for longer is with a step prediction experiment. So as an example, take an LLM on a data set like math, and what we're going to do for these data sets is, instead of just predicting whether it gets the whole answer right, we'll just look at an individual step to see if that step is predicted right. Because typically with something like a math problem, you're usually invoking something from recall, an equation, or you're constructing some auxiliary construction to help you with the problem. And often it's very clear what the problem, the thing is that you should use. As an example, maybe you have to use the triangle inequality, or maybe you have to use, like we said, Newton's second law. So to judge the step accuracy, we can just see whether those tokens are generated. And the interesting thing is, even in a very weak model, so let's say the first generation of Llama, 7 billion, which only got 3% on math, eventually these models generate the right step, often after 5 to 10,000 generations, right? And that's an interesting thought, because I think if you saw like a model like Llama 1 7B and saw they got 3% on math, you just assume it was useless, probably. But actually, with enough inference compute, maybe it can get to a good place. So this is related to that famous idea that monkeys will eventually type Shakespeare. An LLM is actually a bit better than a monkey, because at least it has a tighter knowledge of the kind of like things that human would generate. But here in this example, this is from math. The first step required the model to use a triangle inequality, and we saw that this Llama 1 7B, it typically took like 7 to 10k steps to kind of generate these kind of things. So this is great because it really just tells you that even if you imagine like a frontier problem that maybe GPT-4 couldn't solve, maybe it could solve it if we just pushed the compute a little longer. But I want to challenge this idea, because if you've been following like X, you probably just heard this phrase, LLMs, they need to think longer, and that's like the insight. But actually, I don't think that is the insight. There's actually a clarification. So to give an example, one way to make LLMs think longer is just to do best of n sampling, right? So you take your model and you sample like 1,000 times. But this is very wasteful, as the samples are probably going to be correlated, right? And there's also no memory between those generations of what has worked. So there's nothing to guide the exploration. Similarly for like Monte Carlo tree search, which has some advantages as like a value estimation technique, but it's very wasteful for LLMs in the expansion step if we generate options independently. Typically what you find for some like steps in a problem, the space of options is actually quite narrow, but for some it's going to be a lot greater. But you're going to have the same problem. Instead of like the best of n sampling memory problem on a sample level, you're now just going to get too much correlation on the step level or option level. And again, there's no memory here. So it's not just a case that we want the models to think longer. We want them to remember. We want them to remember what they've tried to guide what they should try next. So this leads to this idea of in-context exploration. So the idea here is to use the context window as a goal memory to remember what has been tried and what to try next. Now this might be too much detail, but another way to think about this is a working memory, which is also sort of the same idea. But the way that humans, one story for how humans solve problems is like through the prefrontal cortex. And one of the key things the prefrontal cortex does is that it has like an order memory of what's been tried. If you want to go even more into the rabbit hole, look up like the dorsolateral prefrontal cortex. It has a memory of what's been tried and what hasn't. And they have an experiment with monkeys and how they perform efficient search. So the experiment is that they have like several doors, and then the monkey has to like search different doors to find where like the reward is. And what they find is when they kind of detach like the dorsolateral prefrontal cortex, is that the monkey search becomes a lot less efficient because the monkey can't remember things it's tried. Whereas like in the monkeys with the correct like wiring, they will actually remember what has been tried to then try next. So this is the analogy here is that the monkey without the DLPFC is essentially like almost like independently and identically sampling different things, right? Which is inefficient. So that's like a best of n planner. Whereas the monkey with the order memory or goal memory, it remembers what has been tried and what to try next. So that's kind of like I guess one source of inspiration. The other key principle is actually using a value network to train when to explore versus exploit. So it's not just a case of trying things and trying other things. You need to know when to stop when something isn't working. As any like ML researcher knows, this is the key problem when you're doing research. It's like, okay, this thing isn't working. Do I just need to push things further, or should I switch gears? So this is like in a way a kind of value estimation. So sorry, a little long explanation, but I just really want to like give some context for this idea because it's quite powerful. So in context exploration, the benefit is going to be when you incorporate memory into exploration. But I would just say one thing to note going forward is that it's kind of an expensive approach. So as you have like larger contexts and you're using the context windows of memory, you're going to have more problems with the compute that you're spending on attention, given the way that attention mechanisms work. So the O1 model by OpenAI, I think it shows some really good examples of in context exploration. You can speculate how they've trained this, but there's probably a few promising ways you could do it. But you see examples where it will do one approach here. So in the first one, it's think step by step, 15 letters. But actually in the problem it says that the example is this. So maybe we should do this, right? So here it's kind of evaluating what it's done and then kind of eventually deciding to shift gears. And then in the second example here, you can see that it's generated other possibilities. So it's kind of branching. So this gives a good example of this kind of in-context exploration idea, but also this idea of these different kinds of like branching behavior or options are kind of implicitly present. Okay, what else? So I'm coming to the end of the talk now, but I just want to briefly mention a direction I think is interesting. So we take a question like which is further to the west, Barcelona or Malaga. So an LLM would solve this perfectly easily, probably because they have some like knowledge of this question in the training corpus, or maybe they could use step by step and they'd remember the coordinates of Barcelona or Malaga or something like that. But this example is good just to think about how you can solve these kind of problems using a different approach. So as a human, if you ask this question, you'd probably hazily have like an image of Spain in your head, and you'd be like, okay, Barcelona's over here, Malaga's over here, and that code would be the basis for like your answer. Another example might be these kind of like shape rotation kind of questions you get in math, or these kind of like more visual questions. So the thing about this is not, I'm not saying that like models can't solve these problems without visual codes. I'm just saying that visual codes like a potential way to reason that we haven't really explored yet. The problem with something like a visual code is that it's very expensive. So like these kind of VQ VAE codes, they're typically like 1,000 tokens. So even with like very large context windows, it's quite expensive to reason in this kind of way. So an exciting direction that I think is worth looking at is, can we get these like alternative representations into more compact codes? So here I have this paper, TikTok, predictably by a team at ByteDads, but they do this really impressive work where they kind of compress an image to only 32 tokens, and it seems to be quite competitive. The interesting thing too is that they haven't really trained this model on like a lot of data, so I think there's a lot of potential for us to kind of overtrain these kind of models. So that would be something that I'd like to see in the open community if anyone has any compute. And this opens up something else, which is like reasoning in entirely new codes. So as language models advance knowledge, I think what we'll see is that existing token vocabularies will become unexpressive, right? So as humans, advance knowledge, they typically generate new tokens to express things. And that's a problem in two ways. First of all, the vocabularies are unexpressive if we need to invent like new mathematics or something like that. But also, as we kind of advance the machine representations, I think we're going to run into a problem where we'll have an interpretability versus performance trade-off. For now, we're in this like really great world where things are interpretable, even these internal reasoning traces that we're seeing. It's very easy to see how a model has come to a conclusion. This is going to be more problematic as we go forward, especially as we get to these frontier problems. We're going to face these issues where we probably trust the answer from the machine learning model, but maybe we don't fully understand how it got there. And that's going to be a key problem in alignment research. So let's conclude. So reasoning requires inference compute. We are unhobbling models so we can use more of it. So we saw how we went from like direct inference to chained inference to reinforced inference, and now to these new kind of models which essentially terminate less and explore more. But the future is beyond text. So reasoning with much richer representations of the world. And that's something I'm interested in, so stay tuned on that. That is the end of this recorded talk. I'm happy to take any questions, or if there's anything wrong in the slides, let me know. I'm on Twitter. You can also email me. But yeah, hope you enjoyed the talk. Thank you very much.